All right, so I'm going to give a brief introduction and overview to some thinking we've been doing regarding application of AI to nanoscale design, and then I will turn it over to Christian Schaffmeister to go into more technical details on both the software infrastructure and the molecular design sides of things. So I myself I'm an AI researcher. I'm among other things, I'm leading an open source AI software project called Opencog, which I'm not going to tell you too much about, but it's a neural symbolic system using a weighted labeled hypergraph to represent knowledge. And with Opencog, we're doing a whole bunch of different applications. So this, apologize for the fuss. This is actually peripheral to the main focus anyway. This happens to be some cool AI things we're doing with Opencog, which is controlling humanoid robots to make realistic facial expressions, to recognize emotion in people's faces, and to hold natural language dialogues and so forth. This is being done in our lab in Hong Kong. And mostly I just wanted to show you that because the robots are really cool. Right? Much cooler than this version of Keynote, which I can't understand at all. No. Okay. All right, yeah, that should be good. So another application I've been doing, which moves a little closer to the event at the moment, is applying Opencog to analyze biology data. So we've been analyzing SNP data, gene expression data, various other types of data. And so this is an example where Opencog looked at a bunch of SNP data related to, in this case, supercentenarians, people living like 110 years or over. And it found a pattern, like if they have a SNP here or a SNP here and a SNP there and no SNP there and so forth, and they're more likely to live a long time. And this is AI applied to data analysis. So having applied AI in a bunch of different practical domains, as well as working toward the longer-term goal of artificial general intelligence, of making AIs that can really think like people, it often occurred to me that it would be interesting to apply AI in the domain of nanoscale design. And of course, you could say, let's just build a human-level thinking machine first, and then let that human-level AGI solve all the other problems. That might be the most rational course. But we don't really know how long it will take to get to a human-level AI that can really solve all our problems for us. And it's also a lot of fun to think about solving nearer-term problems with artificial intelligence. And I knew that AI had been used in many design problems before, which we'll talk about in a few minutes. So to design things at the nanoscale seemed like a problem that would be very appealing to throw to AI systems for a number of reasons, one of which is it's not the kind of thing that humans really evolved to do. I mean, we say recognizing faces, which AI has shown great success at lately, that's something evolution worked on us pretty hard to get us good at doing, because it's of a lot of value to us as human beings. On the other hand, we have not much inductive bias evolved into our brains for figuring out how a protein folds, or how to position like metal atoms on the inside of a tube, right? That's not something humans are tremendously good at. So AIs at least don't have an inductive bias for a totally different domain. They may be much better at thinking about nanosystems than we are. So the type of system I started thinking about is, well, suppose a human being gives some constraints and requirements for what kind of nanosystem they want to build. What molecules or atoms do they want to put together? What do they want the whole system to do? Then suppose the AI searches through the design space to try to find a way to design a system within those constraints that will fulfill the given requirements. Now, one thing you could do in principle is connect the AI to laboratory equipment to experiment with its designs as it manipulates them. But of course, that's very, not only is it cumbersome in practice, but it's expensive to do. So what we want to do in practice is connect the AI system to simulation engines. And there's multiple simulation engines for simulating different systems at different scales and in different ways. There's also an interesting line of research where you use AI to accelerate the simulation process by having an AI simulate a simulator using a deep neural network. And that's sort of new area of research, but in some cases it's been shown that an AI can do what a simulator does much faster after some training. Of course, AI can also be useful to analyze data coming out of a simulator or lab experiment. So what we're looking at here is how would you use various AI algorithms in various different roles integrated together within a coherent software platform to accelerate and improve nanoscale design. And there's a number of different types of AI that could be used here. I'm going to quickly mention 3 of them before turning things over to Christian. So one of them is what's called genetic programming. And genetic programming is a method of automated program learning which emulates the process of evolution by natural selection. So usually what's meant by a program in genetic programming is a little tree. I mean, in this case, this is a program with pluses, x's, and 2's. It's simply a program that evaluates this algebraic expression, which is very simple. You can also have programs that contain operations, like, okay, this is the end of a bond, we're inserting something here, we're adding something there. You have a program where as you execute it, it builds some structure. And Christian will talk about some pertinent examples of that. In general, whatever kind of program you want to learn, the genetic programming process works by taking a population of possible programs, evaluating how good they are at doing something, selecting from among the ones that did well, mutating them, crossing them over, maybe using some other operations. That gives you more programs in your population. And then, similar to evolution by natural selection, you're trying to evolve new programs. And this particular type of AI has proved very good at designing various systems. So I think it's highly relevant to nanoscale design, as Christian will go through in more detail. There's been recent work, as I mentioned, which is a different application of AI, but fits in the same framework, using neural networks to accelerate physics simulation. And Josh Tannenbaum and his colleagues made something called the neural physics engine, where they take a physics engine as used in a game engine, so Newtonian mechanics on solid objects, and they show that by using a neural network, you can do the same calculations that the physics engine does, but much faster. So in essence, each little configuration of solid objects in the simulation, from studying many different simulated scenarios, the neural net figures out what's the most likely future of a given configuration of solid objects. Then it can, in effect, jump ahead many simulation steps in the physics engine, and the neural net can do faster simulation than the game engine. Now, applying that to the more complex simulations involved in nanotech is certainly not trivial, but it's the same form of problem. And I mean, this research was just published at the very end of last year. This is kind of new, hot off the presses stuff. Another area, which is something I've worked on a lot, is application of automated reasoning. So we have a lot of equations in chemistry and physics. We have a lot of formalized knowledge, and you can use AI to reason on that formalized knowledge to draw new inferences, new hypothetical conclusions. And this can be used, this hypothetical knowledge can be used to guide evolutionary design. These different types of AI can all work together. And there's a lot of depth here in the AI, which I'm not going to go into now, but I think it's a very important thing for a number of reasons. I mean, we see now increasing enthusiasm for AI in many different areas, and a lot of the energy and money is going into applying AI to problems that maybe in the grand scheme of things aren't the most important problems. I mean, like historically, most AI funding was military. Now most AI funding is pretty much going to trying to get people to click on ads on the screen while they're surfing the web, right? Which is something. I mean, it funds other interesting projects that these big tech companies are doing. On the other hand, there's huge potential to apply AI to things like, designing new drugs or designing catalysts, designing new types of materials, which are arguably much more important for the future of humanity than putting ads on web pages. But due to the way the economy works, there's just a lot less focus on these, these life-saving, world-changing applications of AI. I'm focusing on the AI algorithms part, which is really fun for me. Like, I'm developing all this AI in Opencog. I'm dying to apply it to nanotech as I am to biotech and robotics. But in order to get started on that, there's a lot of nitty-gritty work that has to be done to make that easier. So what Christian's going to start off with is talking about a software platform he's been developing, which is called Can-Do, and it is very elegant and allows integration of different simulation engines, different data processing software, and will allow integration of different AI software, although we haven't done that yet, into a common platform. So he's going to talk a bit about that, about his work applying that to molecular design, and then if we still have time, I may induce Steve to come up and talk a bit about how you could apply the same type of tool set and software framework to different level of nanotech, where you're doing atomically precise positioning and building things with metal atoms instead of the larger molecules that Christian is working with. So, yeah, now Christian will take over and talk about some very exciting work that he's been doing, which already realizes some of this vision, and which I think we can use to realize the rest of it.
Continuing that, to change gears here. So John Koza was speaking this morning about genetic programming. I got my first sort of presentation on that. So he's sort of the father of genetic programming. He wrote the book on it, wrote several books on it. And one of the interesting examples that he showed was how they use genetic programming to design circuits. And this is something that I've been interested in a long time and sort of wanted to learn once I got to the point where my other systems were in place, but to use AI for molecular design. So what I'm going to talk about is just two ideas. I hate to present more than one idea, but I'm going to present two ideas. One is, I've got a software package that can help everyone do molecular design. I've also got a set of molecules that are very amenable to design, that let us design functional molecules with them, and the two of them together are going to be like a Reese's peanut butter cup. The applications I'm working on are to develop new medicines, new catalysts that can accelerate chemical reactions and make new products and do things like pull carbon dioxide and water out of the air and sunlight and knit it into hydrocarbons to take the CO2 back out of the air and pump it back into the ground, and to make atomically precise filters. So to do genetic programming to design molecules, this is what I believe you need to do. You need to do it using evolutionary techniques, where you basically have a starting structure of a molecule, you build a three-dimensional structure of that molecule, you score how well it can organize groups in space, and then you mutate it. And then depending if it scores better or worse, you keep it, or you go back to the previous design. And by doing that, you evolve your way towards an optimal design. To do this, you need to bring a lot of functionality together into one processor. You need the scoring function, you need building tools, you need a lot of software in one tight loop. And so it needs to run in one processor. And basically, I think it needs a molecular programming language, something where you can integrate all this stuff together in a very tight software package that will run in a very tight loop to do this. The molecules that I have been developing to do this, I think are much more amenable to design than most other molecules that are out there, are these things. We call them spiroligomers. They're building blocks that have a cyclic core and then two amino acids, one on one side, one on the other side. We can hang a functional group off of each building block that's like the side chain of an amino acid. When you link these to each other, they link through pairs of amide bonds. This is completely unique. There is no other chemistry out there like this. And you get these complex three-dimensional structures that are kind of like sticks with functional groups hanging off of them, like protein, amino acid side chains, but we can choose side chains from the entire chemical toolbox. Some of the things we want to do and apply evolutionary techniques to evolve molecules is drug development. So this is a protein, hemagglutinin. It's on the surface of our cells. And if you could make a molecule that could bind into this groove here, you could prevent, oh no, actually this is from HIV, but it's a protein that if you make a molecule that binds into this groove here, very shallow groove, you could prevent HIV from fusing with human cells and it wouldn't infect human cells. So a molecule that I would design to do this would be one that looks like this, a whole bunch of our building blocks strung together, connected through pairs of bonds. Every one of these labeled carbons here is a stereocenter that could be S or R, point groups in or out of the board. Every one of these side chains can be chosen from 100 different side chains. So there's an enormous design space here. You can imagine just randomly picking side chains and stereocenters, docking it against the protein and pulling it away in a calculation to determine how tightly it binds, and then mutate a side chain and then do it again. And if you use evolutionary techniques like genetic programming, you could have thousands of these molecules, run simulations in parallel, and then use sexual recombination to mix and match them, and then try it again and try and optimize towards an optimal molecule. Then you go make it and see if it binds the protein. The molecules have great drug properties. They're not going to be touched by proteases. They won't raise an immune response because they can't be displayed on MHC proteins. Synthetically, they're very straightforward to put together. So we've been developing these molecules for about 15 years. Another application is Catalase. So here, take the same kind of building blocks, different functional groups on the outside, synthesize these little three-mers, and then stitch them together like a peptide. So it's just 4 of these linked together. We cross-link them at the top using additional chemistry, and we present metal binding groups off of different locations. So you get this thing that's like a book or a clamshell. And if you throw a metal in and everything's designed properly, then it could bind to the metal and have a pocket where substrates can go in and react only one way because they're controlled by the shell. It's like an enzyme active site. We can make trillions of these. We have a big design problem here, lots of stereocenters to control, lots of functional groups. So we need some sort of, we can't make them all. We need some sort of AI design tool, and that's what I've been developing. But I think these molecules could be used to make enzyme-like catalysts. You could do things like convert methane to methanol, for instance, which would just change how we produce energy. Another idea, this is something I'm working with the Army Corps of Engineers. They're very interested in trying to mimic aquaporins, the proteins in our cells that regulate osmotic balance. So we've already synthesized little triangles like this. And then what we hang down are these long sort of processes, and then we're going to link them up on another triangle at the bottom to create a thing that's kind of like a barrel, a triangular barrel. And with the software that I've developed, I can build these molecules very quickly, build a two-dimensional network of them, pop them into a box of water on the top and the bottom, and then with the Xementiev group at University of Illinois, they run dynamic simulations on these with NAMD, and we can calculate the flux through this membrane. It's about the thickness of a cell membrane. And then we can mutate the internal structure and then see how it changes the flux and computationally design molecules to, water is one thing, but other organic solvents, and I especially would like to make big channels that could be used to separate small molecules. I'd love to be able to make a filter that can separate my building blocks from each other and then have a box where I can just do the crude chemistry, which generates a mixture of building blocks, and then run it into the box and have 4 pipes coming out with the purified building blocks. This is something that's conceivable with membranes like this. So what this needs is really new software. There's lots of software engines that, that are basically C++ libraries that do molecular dynamics or DFT calculations, density functional or quantum mechanical calculations. I don't want to rewrite those things. I want to use them. But the way you have to use them right now is you have to basically set up a file, run the program, load the file, run the calculation. It writes out a file, and then you have to write another program to analyze the results. And it's very slow. It's not amenable to this sort of tight building loop that I want to do. So what I've been working on, and we've been talking about how to integrate these programs into a unified sort of single executable that could have lamps inside of it and tools to build molecules, and then do this molecular design using lamps or using amber or using any of these sort of molecular simulation programs. And what you want then is something where you can give it, sort of write a program that describes the requirements of a functional molecule and then run it through the package, and it'll give you a sequence of the molecule that when you synthesize it has that function. So I've been developing a big software package like this. It's called CANDO, and basically what it is, it stands for Computer-Aided Nanostructure Design and Optimization. It is a programming language. It's basically a whole bunch of chemical functionality that manages atoms and molecules and residues and stereochemistry, force fields, automatic type assignment, automatic charge assignment, and it's all written in C++, but it has within it a common Lisp compiler that I've written myself that generates fast native code. And it is all based on C++ and LLVM, the library that makes iPhones, and everything that's on a Mac is compiled with the LLVM library. So CANDO and CLASP generate LLVM code, and that allows this. You can basically take C++ or C or Fortran code, compile that code into this intermediate representation that LLVM uses. Common Lisp is also compiled to the same intermediate representation. So you can link code together from C++, Common Lisp, Fortran, and have it all inlined within each other to generate code that runs as fast as possible, that has no barriers between, as little barriers as possible. So this is the big sort of central engine behind the CANDO. LLVM is being developed by Apple, by Google. It's a Sony PlayStation 4. It's a very powerful compiler writing library that's built into CANDO. So the way we're going to be releasing CANDO in the next couple of months. Basically what it lets you do is like go into ChemDraw and sketch a molecule you want to design. This is a cyclic molecule that has our little building blocks on it, and I want to hang a group off of here and here and here that can all point to the same side, because what I want this molecule to do, and I'm funded by the Department of Defense to do this, is to coordinate a zirconium oxo metal cluster that can hydrolyze nerve agents. They want catalysts that can hydrolyze nerve agents. So we want to make something that can coordinate and sandwich this metal cluster to protect it so it could act like a soluble enzyme. And so we need a molecule that points these three groups on the same side at the right distances from each other. So the things that we can control are we can change the stereochemistry here, 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 here. We can change what group we hang off there, 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 here, here, and here. And so we have a lot of variables that we can mutate. And the way I'm setting this up is I can load that ChemDraw file into CANDO, that's what's running here. The user interface is what's called a Jupyter notebook, and you can write a code in CANDO that will like build every stereoisomer, do energy minimization on it, calculate whether the carboxylic acids that are generated match up to where they would need to be to bind the zirconium oxo cluster, and then iterate through them all, and then save the best fit. So you see the result of the calculation. The input and output here, what we're doing right now is we're getting the widget stuff to work inside of the Jupyter notebook, so you can sketch the molecule in here, run the calculations, and then see the structure down below, and it'll provide a very nice user interface for setting up and sharing molecular calculations. And you can design all sorts of molecules with this. Anything that's made out of atoms is what this thing is designed to help you build, model, and design. I hope if that answers the question. I'm pretty much done there.
Chris, do you want to do discussion now, or do you want to wait till after Steve?
I'd be happy to answer any questions.
Let's do some discussion now, both about your presentation and also Ben's. Where's Ben? He's right here. So we're supposed to offer helpful suggestions and comments, right? Pretend that that they were pitching to you. It's your job whether to yes, Gail, you have a comment.
Yeah, question. You mentioned functionalizing for nerve agents. What are you thinking of in terms of an application?
Hydrolyzing nerve agents, detoxification.
In what sort of setting? In what sort of setting? In what sort of?
Everything from spraying tanks to detoxify them. Like if they've been exposed to nerve agents, a bomb goes off and nerve agent gets spread all over the place. To be able to spray it with catalyst so that it hydrolyzes it all and it's now safe to touch. To injecting it into people who've been exposed, you have a very narrow window there, or prophylactically injecting into soldiers who might be going into a contaminated area where the catalyst could hydrolyze the nerve agent faster than it can get into their neurons. And that's what we have support right now to do that. And the reason, I mean, the Department of Defense has been putting a huge amount of money into developing enzymes that can do this. But the problem is formulating, storing, delivering enzymes is just a nightmare. Those things they're fragile little snowflakes that fall apart when you look at them the wrong way. They unfold. Proteins are fragile, recyclable. The molecules we make are pretty much indestructible, tiny. They can get into places where enzymes can't. What the Department of Defense wants, what DITRO wants, are abiotic, non-natural approaches to hydrolyzing nerve agents. And we've got a couple of ideas on how to do that. One, mimicking some enzymes that hydrolyze nerve agents. Another one is taking this zirconium oxo cluster that the HUP group at Northwestern has demonstrated in metal organic frameworks is quite active, very active, and turning it into a soluble form, because you can't inject MOFs into people. They're crystals. They're crystals. You don't want to inject that in people's bloodstream. But a soluble form that's 3-4 kilodaltons in size would be very, very useful. Yeah.
Okay, Jeremy.
So this is a beautiful design system for your molecules, and it seems like you could extend it to a huge range of systems. How easy is that? I mean, how much work are we talking about to take the platform that you've built here and extend it into designing nanomachines of, say, Stoddard's type?
Stoddard's easy. Building a ring and sketch. All you'd have to do is with a new user interface that we're going to get working in the next couple of weeks. You would just sketch it like you would in ChemDraw, and then say build the three-dimensional structure of this part, put the ring over the thread, and you'll have a molecular model that you can then run a dynamic simulation. And we'll get lamps in there, and then you can run lamps on it without writing it out to a file and then shutting it down and starting up another program. So that's easy. Designing things like peptides or peptoids or other more flexible floppy molecules is hard because you have these huge conformational search or space that the molecules can access. I think it'll be great for setting up simulations. I've designed these molecules this way so that they are easier to design because they have well-defined shapes that I can predict.
So what if you take it the other direction? What if you have well-defined shapes but millions of atoms?
I'm working on a project right now to design DNA or get atomic level models of a DNA origamis. So there's something where you could get a shape, but it'll have 40 million atoms in it. This thing can do scales. It scales to 10. I've loaded 10 million atom structures into it, no problem, because it does the memory management, all that hard stuff. It does it properly right from the ground up. So you can build and manipulate very large structures. Why I've been going off on Python all weekend. There's a program called PARMED. I don't know if some of you know this. A program for translating input files for different molecular dynamics packages. It's written in Python. It's great. Lots of people love it, but it doesn't scale. You can't put more than 10,000 or 100,000 atoms into it, or it takes several days to load the file and process it and write it back out again, because it's written in Python. The stuff I've written is written in C++, LLVMIR, native code, everything linked together, inline together, so it runs fast, scales, and you can handle tens of millions of atoms.
So this is a very, very exciting project. I think it really makes a lot of good sense. I think we need to tie in the quantum mechanics, like Sebastian put one end,
Yes.
hydrodynamics at the other end. In between them, you have chemical reactions that go on, and you can do that with VASP, but that's 300 atoms. So you might think about using reactive force fields that can scale that up to a few million atoms.
I want,
So,
but I don't want to implement the force field again. I want to use your code. That's why I asked about it.
Put it in lamps, so it's,
Yes.
it's in there with, so you can start using it.
And LAMPS is a C++ program,
Right.
so we can take the C++ code. Candu has built within it the ability to read C++ code using the Clang compiler and automatically build an interface to it. So I could get LAMPS into Candu in a couple of days.
Yeah, so it's LAMPS has a lot of different codes implemented in it, and they all have different kinds of pair styles and different details. But,
Yeah.
but the point is that you can sort of, you can check it out with quantum mechanics and look, make sure about barriers like that, and then you can scale up to a few million atoms to maybe get a more complex system and make sure that there are no issues in terms of barriers and stuff like that. So it's
Yep.
a really great plan. Really
Yeah, I mean, so from an AI view, I mean, the same AI algorithms can be used for.
So
the-
Opencog is C++.
Yeah, Opencog is C++, which happens to have a Lisp wrapper anyway. So, I mean, the same AI algorithms can be used for the types of molecules you're working with, and for more
and-
atomically precise positioning, Stoddard-style machines and so forth. So, and
And the AI can also help improve all these force fields. They handle reactions, but
Yeah.
when you go into practice and actually make things, you might find some changes in it, and you'll be able to use the AI to
Yeah.
help identify where there's some less accuracy that you can then improve.
also true. I mean, so as an AI developer, to interest other AI developers in trying out their tools on nanoscale design, it's important to have as simple and unified a platform as possible. I mean, AI developers don't mind dealing with Lisp or dealing with various kinds of software, but they don't want to have to understand
Right.
the details of different simulation packages and so forth. So having a sort of unified interface for different types of nanoscale design problems is key for getting the AI community engaged in this kind of work, because they just don't have time to become really knowledgeable about
A
each
good
kind of
overall plan
nanosystem.
here, combining these elements together might actually make it work.
There's one other aspect. Chemists are going to be, I think, a little resistant to learning Common Lisp, but there is a Python implementation in Common Lisp that we can just compile into there, and you'll have Python, but it'll be able to access all the C++ and everything seamlessly. So we can have it all. We can have our cake and eat it and share it and everything. It's all C++, LLVM. I think it's going to be a really great sort of molecular design, molecular programming environment.
Any other, okay, one in the back, Steve Burgess.
These prophylactically injected structures in solution for soldiers for the purpose of detoxifying toxins. How do you assure that they don't themselves, while they're floating around, bond with something that creates a toxin?
So because these are rigid structures, they have groups that stick outwards, they have groups that stick inwards. We can change the functional groups on the outside to change the solubility and what they might bump into. And we don't have to worry about how it's going to change the inside because everything's rigid, stiff. And if it does stick to something, then we'll just change the outside so it doesn't stick to that thing. And then, but we can preserve what it does on the inside. I mean, it's kind of, we can resurface these molecules without affecting what the internals look like. And they're all just made out of carbon, hydrogen, oxygen, nitrogen, CHON. This is the stuff we're made out of. It's safe. It's not toxic.
But lots of bad things are made out of that stuff too, right?
It's hard to make something that's, with big structured molecules are highly selective in terms of what they interact with because they can't change their shape to stick to things. That's one thing that's sort of come out. Like the solubility of our molecules is excellent. We purify them in water acetonitrile, because they're sort of stiff and weirdly shaped and they point groups out in weird directions and they're just not compatible with themselves or anything else. And so they stay in solution. That's one thing that we've seen.
Capture stuff and not do anything else.
You have to design them to bind specific things. You really have to work at making them bind something.
That's how you remove them from the body.
You could do that. You could remove them by making something complementary to pull them out, like dialysis sort of pull them out. But they're indestructible. But they're small too. The other thing about them is we could make a catalyst that's like 3-4 kilodaltons, and it'll be cleared out in the kidneys. Anything less than 50 kilodaltons is just flushed out. So you're just gonna, pardon the expression, you're just gonna piss them out. And we can make them water soluble. So I think they'll have great properties in the body. I mean, we've thrown them at cells, they don't hurt them at all. Yeah.
Okay, other questions or helpful comments, critiques? Okay, now, we have a person who just walked in like 2 hours ago, so I'm putting it on the spot. Do you have any suggestions? You look at a lot of proposals. Any suggestions for improvement, comments, questions? You don't have to, but.
Well, having just heard it last 10 minutes, no. I think having been through the process of in biotech with drug delivery, it's a long way from we can put it in the body to it's going to work. A lot of things happen. So what do you see the development process? At least what does the DoD see as the development process? I mean, this is a long-term project, right? And I'm assuming that you're in an early stage.
Yeah, we're sort of tier, technical level 1, 2, 3 here, TR, and we're not really worried about getting it into the body. The molecules themselves I think have inherently good pharmacological properties. We have not looked at that. It's kind of putting the cart in front of the horse is what I think. We need to demonstrate catalysis. With nerve agents, you're gonna die. And so they're developing enzymes that could protect, and they have a prophylactic effect in guinea pigs. I go to these meetings, they show people injecting guinea pigs with nerve agents and stuff. And the enzymes that they have are quite active. They will have immune response. They will have all sorts of problems. They're not too, they're more focused right now on just detoxifying things. Let me reword that. We're developing a lot of applications where we don't have to go through clinical trials. We don't have to go through that kind of stuff right away. Catalysis, we don't have to worry about it. Channels, we don't have to worry about it. Catalysts for detoxification, where you're just going to spray them on the tank, we don't really have to worry about it as long as they're not themselves very toxic. So I'd like to discover some molecules that bind proteins very tightly. We have one. And then if it looks like a good drug candidate, I'd definitely like to go and explore the pharmacological properties of these molecules. That's kind of going to have to happen another day.
So we talked earlier that you can build channels potentially. So I think there's interesting applications of that are actually inserting channels as human aquaporin into organisms. So as an example, into bacteria, for example. Or even into plants, increase either gas exchange or whatever. So, and I think, one thing that you're always thinking for applications, but I think from the kind of basic science level too, that you have interesting systems that could be put together with, with biological systems to study the biological systems themselves. So,
yep. So this is why we make them thick, is so they could span a lipid bilayer as a sort of a starting point. And we could put greasy groups on the outside And I think they would just go right in and hold open a hole.
And you could determine orientation?
Uh,
Get it to orient the way you want? You think you could have selective transport?
Yes, I mean, because we can put all sorts of groups off of them to give us selective binding, but that is a design issue that has to be sorted out. But yes, absolutely, they are asymmetric. I mean, the top is different from the bottom, and so there should be a selectivity on how they go in. So.
And the question is, could you regulate something going through either one way or so selective?
With more complex structures, having moving groups inside that can create selective channels that close and open, and even pumps are possible. I mean, proteins do everything like this. With big enough structures, I'm sure we could do that. It's going to take a lot of engineering and design.
So
that's
is
where
that within the realm of you being able to scale up to that, do you think? So you're laying the kind of the groundwork for that.
Yes. Oh, yeah. We have the synthesis of these are all sort of convergent. So we synthesize segments and then we link them together, and we try and keep the number of linear steps short because you lose every time you do chemistry. This is one of the tragedies of chemistry. And I think we can assemble large molecules that are 5, 10 kilodaltons fairly straightforward. Beyond that, it's more synthesis. Yeah, I mean, for membranes, this stuff really scales. I mean, 5 grams of this stuff would cover a football field of membrane. Catalysts, if you make active catalysts, a small amount can generate a lot of product. Yeah.
Okay, any other comments, suggestions, critiques, complaints about this proposal? Complaints? No. Well, thank you, gentlemen. Let's give them a hand. Good job.
Thank you.
Okay, we've pretty much reached the end. So, yes? What? No, he doesn't want. All right. So we've pretty much reached the end, and